Hello everyone. So in this video we are going to learn about splay trees. Splay trees are one of the very interesting trees and are used in many of the applications. Let's start. Okay, so splay trees are a kind of self-balancing trees. They are not strictly balanced like we have already discussed AVL trees and the RB trees. They are a kind of fully balanced trees. Splay trees are a self-balancing trees which tends toward making themselves balance as we do operations on it. So we talk about the complexity of the binary search tree. So splay tree is also a binary search tree, and the average case in the binary search tree is log n if we assume that the tree is almost balanced. So all the operations on the balanced trees, or you can say all the operations that we do on the trees are depending on the height, and the minimum height that the balanced tree maintain is log n. So here we can say the average case for any of the operations that we do on the balanced trees or binary search tree is log n, or if the tree is skewed, that is, it extends only in one direction, then the cost of the operation is big O of n. So if the tree is fully balanced, like in the case of ABL and RB tree, that is log n. So what exactly we are doing in the splay tree? The splay tree is basically doing for us a kind of caching activity, which will bring all the items which are frequently accessed closer to the root. So what is the impact of this activity? So the impact of this behavior is, we assume that generally when we perform some operations on any applications, uh, we generally tends to work on a kind of particular data set. So if uh, this is the thing which is observed, that only a particular set of data we have been using on at any point of time, then the display tree is a fantastic kind of data structure to be used, because all these items that are to be frequently accessed are to be brought closer to the root, because every time when we access any data items onto the display tree, it will bring to the root. So all those elements which are to be accessed are becoming the root or to the nearer to the root. So when we access these items, will be accessed faster, because all the operations that we do on the tree starts from the root. So if the elements are existing near the root, then they can be searched easily and all the operations can be done in a quicker time. So if we look to the applications, that what are the applications where these split trees are used? So basically it is used for caching. So caching means whatever the items which are used frequently, they are brought very near to the root so that they can be accessed faster. Uh, this is also used in dynamic order statistics. Uh, Basically, in order statistics, uh, we can efficiently find any kth smallest or largest element among the dynamic set of elements. So this is one of the areas where this kind of split trees can be used. Network routing is another uh, prominent area where split trees can be used. You know that router maintains the routing tables, and these routing tables have keep changing due to the change in topology. If any packet to be sent to any address, then these address to be searched in the routing table and then the packet to be forwarded. So if any particular IP has been used, then we can assume that this IP or a set of IPs which have been used in a shorter time to be used frequently, and they can be put in a- arranged in such a way so that they can be accessed very fast. So again, we can use this split tree concept so that a set of IPs or a particular IP can be kept closer to the root, so that the IPs can be searched faster and the packet can be transmitted in a faster pace. Data compression is also one of the application where the split trees can be used, and it is widely used uh, in algorithms like Huffman coding and adaptive Huffman coding. So these are the different areas where the split trees can be used. So let us talk more about it. Now look to the characteristics of the split trees. So as I said that whenever anything to be searched from the tree, then that element will move towards the root. So if any tree is given to us, let's say this is a tree, which is a binary search tree. So if this element is being searched, then we will do splaying. Splaying means this node will be going and becoming the root. And let's say if you are next time if you want to search this element, then this element is going to be moving upward and going to become the root. So in the next time, if you search this element, then it is also going to becoming upwards, going to the upwards and becoming the root. So what is the impact of this? That all these three elements, after three operations, are existing into either the root or to the nearby the root elements. So we are assuming that these are the items which need to be frequently accessed. So now after the three operations, these elements are to be found out at the root or near to the root so that it can be accessed in a faster way. So if you look entirely that what is the cost of these operations, so if we look closely to it, and we will realize that here amortization can be done, and with the experiment, and it has been found out that the amortized cost of this split tree can be found out to be log n, because initially you may be doing uh, kind of operations which may be costly. If this is going to be 10, for example, if you're going to make a tree which is going to become like this, but when you do splaying, these elements are moving towards the root, and also when we are doing splaying, the tree is tends to become balanced, and when the tree is tends to become balanced, the cost of operation is going to become log n. So here you can see that it will use potential function that says that initially we are paying much cost to the initial operation, but when these values are moving towards the root, then the cost becomes very very cheaper. So if maybe initially you are doing operation of the cost n, but then after some time, when you do multiple splaying operation, then to access these frequent items, the cost may be equals to the constant. So as a whole, when we do all the calculation, the amortized cost comes out to be a log n. So in order to understand that how the splaying works, we need to understand how the rotations are performed in the splay tree. So splaying is a term I am using that means that we are moving the element or any node to the root. That is called splaying. So rotation 1 is a simple rotation that we have already discussed in the avian and arbitrary. So simple rotation, if I want to splay x, then x is going to move towards the root, means x is going to move here and y will come down, and you can see this is a straightforward. When we do zigzag, zigzag and zagzag, that means we have this kind of structure in this direction or in this direction. This is called zigzag and zagzag. Or if this is the scenario where we have this kind of structure, this is called zigzag or zagzag. Okay, so rotation 2 basically refers to zigzag or zagzag. So here we are doing a series of operation. So here x is here and the root is actually appearing here. It is not immediately after at the parent, but it is at the grandparent. So here what we are doing, when we are having a zigzag or zagzag kind of structure, whenever we do rotation, we do in pairs. So we don't do the rotation at the parent, but we are doing at the grandparent. So what is the impact of this? If you look at this structure, if you have this x, y, and z, then actually this all goes down to become x, y, and z. And how do we manage the subtrees? So you can see there that it will going to work like this, that this b becomes the left child of y, c becomes the left child of z. So you can see here, so it will come down and this all moves up. So c becomes the left child of z, b becomes the left child of y. And similarly, if you look at this is going to means this structure going to become like this, And also here we see the same kind of pattern that C becomes the here because we are doing a left rotation. So this left child of this becomes the right child of this. This left child of this becomes the right child of this. We move to the rotation number 3, that is zigzag, where you find this kind of structure. This kind of structure is fine. So here, when we want to make a rotation, as I said that we are doing a rotation in pairs, so actually it is to be done at the grandparent. So this is actually straightforward. If you look at this, you will find that x goes up, this x goes up, this z goes down, and this right shall become the left of this left shall become the right of this. That means, let me draw it here. So x will go up, x will go here, this y will remain same, this z will come down, and then this is d, and this right become the left here of this, and this is a, and this left becomes the right of this. So this what we can see. And the other thing that you can notice here is that after the rotation, this is the tree with height 3, but now it becomes height 2. That means after the rotation, it also reduces the height, and it also it makes it's more balanced than the previous one. So when we do this kind of rotation, also the tree is actually moving towards the balancing structure. Okay, so having understood all these three rotations, now let us see that how these rotations can be worked on any uh, tree. Also, we need to see one thing that if we say move to root operation means here we trying to move towards the root uh, one at a time. Means if we want to make the B move the root to E, means if we want to make B becomes the root, then first we will move B to C, then we will go from here to here, then we will go from here to here, and then we will go from here to here. That means you are doing a series of 4 operations. But when we do splaying, so splaying will require 2 operations. So it will directly from this position to it will come to A, and from A it directly go to E. So if we look to So if we look to this structure or this sequence of steps, this is just a move to root state shown to us, where B just moving one step and trying to become the root. So if you look at this, so first you move from B to C, so that you are doing the right rotation. So B will come here like this, and then B should come here. So you do your left rotation, and so B will look like this. But if we do splaying of this structure, then we don't go like this, but B will directly go to here. So what is the structure that we go? So as we have discussed, this is a zigzag case. So here we will find that B will go straight forward to here, and A will come here, C will be here. This is 4, and the right of this becomes the left of this, and the left of this becomes the right of this. And then we have D, then we have E, and this is 5, this is 6. And then again, we can directly move B to E here. And so when you do like this, then actually you will make like this B, and then D, and then E. So E will be 6 here, and this right of this becomes the left of this, and you can find that the right of this becomes the left of this, C, A, and the rest of the tree will remain like this. Okay, here we have missed this. This is actually here 1. This will be here 1. This is called a splaying. Here you can find the difference. If we do case 1 means this x is just below the root, means you have to only make one rotation. So if you do the splay x and the move to the root, it is the same structure. Similarly, in the case 3, when we do a series of operation, so if you want to make x to become the root, then you are doing series of operations. So you will be, if I say move to root, so x will come here and then x will go here. Finally, you will find the same structure. If you are doing a split, then also you get the same structure. But when we have a case 2, that is a zigzag or zigzag case, in this case, if you are going to do splash, if you are going to do splay to this node X, then you will get this structure. But if you are doing step by step, moving one by one steps towards the root, so if you move X here first and then you will move X here, then you will get this structure. So case 1 and case 3 will give you the same structure, but in the case 2, the structure is different. So let us try to understand and apply the splaying on this tree. So this is splaying, and A means we want to bring A to the root. So let's see how it will work. Let us make more space for us. So look at this. We want to splay A. So here, this A is going to come here. So because we are doing in pairs, it will not go to immediate parent, but it will go to grandparent. At A, and then B and C, and then here we have 1, and then right of this become the left of this, and then we have 4, and the right of B becomes the left of C, and here we have remaining D, E, F, and G. So D here we have 5, E here we have 6, E we have 7, and this we have 8. Okay, so this is the status. Now again we will do splaying. So this A node we want to splay, so it will go to E here. Okay, so what is the impact of this? So look at this. So we'll get A, and then we get D, we get E here, and so you can see that the right of D becomes the left of E. It is 5, and 6 will be here, and the right of A becomes the left of D. So we have B here, and this will remain the same like this, and A1 we have, and the above tree will remain like this. We have F 7 and G 8. Okay, this is what we have get after making two splay operations. Now the A should go here. Okay, so let's see what is the structure we get. So we'll get A, then F, then G. Now this right becomes the left of G, the right of A becomes the left of F, that is the right of A becomes the left of F, that is D, it is E, 6, 5, we have B, C, 2, 3, 4, and we have 1 here. So we have 1, 2, 3, 4, 5, 6, 7, 8, and A, B, C, D, E, F, G, and we are able to get this at the root. So this is how we are doing splaying. So here we did one operation, and then so one operation when we do, we get this thing, and then we do second operation, and then we third operation, and only 3 operations are required to bring this node at the root. This is all about splaying, and I hope that you understood how to do splaying on a tree, and also you understood the applications of splay. This is all for this lecture. Thank you very much.